Good morning. I'm Ambuj Vashne, and I'll present our work titled Directional Transmissions and Receptions for High-throughput Bulk Forwarding in Wireless Sensor Network. This work was done in collaboration with Luca Motola, Matt Carlson, and Timo Fock. So we begin our presentation by asking what is a directional antenna. A directional antenna radiates or receives greater power in a specific direction. An electronically steerable directional antenna, or an ESD antenna, is a type of directional antenna that allows electronic control of the direction of the maximum antenna gain. One such ESD antenna is shown on the slide, which is the speeder antenna which we use for the experiments that we conduct in this paper as well. This antenna has 6 configurable antenna directions, and it cost only less than $5 to make. However, if you look into the directional communication and the directional antenna, they have been extensively studied over the past many years. However, most of the existing work is limited to one-hop networks like the Wi-Fi or the cellular networks. Wireless sensor networks are inherently multi-hop in nature, and they present a very different challenge as compared to the one-hop networks. And most of the existing work with the directional antennas in wireless sensor network is only limited to the directional transmissions and only at the sender side, and even this is only in simulation. So if you look into multi-hop links, they are primarily affected by the interpath as well as the intrapath interference. The intrapath interference occurs when the transmission of the same packet by a successor node interferes with the reception of the next packet. For example, in the slide, we have a small network topology where S is the source node and D is the destination node, and we want to transmit packet from the S to D. So at the time t equals to 0, the S sends a packet to the intermediate forwarding node. At the next time instance, it forwards a packet to the next hop node, and then it forwards a packet finally to the sync node. If you see the transmissions here, TX1 and the TX2, these two transmissions happen at the same time. And these transmissions, the transmission TX2 could interfere with the intended transmission TX1. And since this is part of the same path, this is called the intrapath interference. It is also possible that the two separate flows, they interfere with each other. Here in the slide, we have the nodes in the red color, which are part of a separate path, and the nodes which are in green color, that is another path. So here the transmission TX2 from the red path interferes with the transmission that happens to the green path. And since these are two separate flows, this is called the interpath interference. Now we know that the directional communication reduces the channel contention. So the directional communication or the use of the directional antenna should also reduce this intrapath as well as the interpath interference. So in spite of these advantages, why are ESD antennas so unexplored in wireless sensor network? This is not because of the feasibility or the cost involved. As we had seen in the earlier slide, that they are extremely cheap in cost as well as they are very simple to make. These have been unexplored because these are extremely challenging in a multi-hop network. For example, if there are k configurable antenna directions, there are k-square links between every neighboring node in the network. For example, in the speeder antenna that we have, there are 6 configurable directions, which can result to the maximum of about 36 links between every pair of neighboring node in the network. And this makes the design of distributed algorithm extremely challenging because of the scale of the problem, as well as the fact that the decision needs to be coordinated across multiple hops, as the choice on a given node may influence many other, even multiple hops away. And this is, for example, why in case of directional transmissions, hidden terminals are more likely to occur. So in spite of these challenges, the ESD antennas could be extremely useful for class of wireless sensor network applications which require bulk data to be transmitted. So some of the bulk data transmission is a traffic pattern which is common to many wireless sensor network applications. And these applications include applications like volcano monitoring or the bridge monitoring. A central feature of these applications is that there are a lot of sensor nodes that are deployed which collect large amount of sense data, which could be at the order of few tens of kilobytes. And this needs to be communicated over multiple hops to a sync node for further processing. The directional antennas could be extremely useful for such applications as they increase the communication range at no additional energy cost, as well as the bulk transmission occupy the channel for a large period of time, and hence the ability to reduce the interference could be extremely useful for such applications. However, there is no existing protocol support in wireless sensor network to exploit these features of ESD antennas for bulk data transmissions. And this is where our contribution comes in, which is the directional pipeline transmission protocol. So this leverages both the directional transmissions and receptions for bulk data transmission. We show that the directional transmissions together can reduce the interpath as well as intrapath interference significantly, which our results demonstrate that allows high throughput multi-hop transmissions on using only one wireless channel, which is very important right now because there are so many devices that operate on the same ISM band, and interference is a big problem. And finally, what we also show is that we, using our protocol, achieve the highest throughput that has been reported over 802.15.4 multi-hop links. So the first question is, how does the DPT protocol achieve high throughput? So our protocol, it uses pipelining to achieve high throughput, like the other bulk forwarding protocol that also use pipelining. However, if we only have a single pipeline, it can only achieve 50% of the maximum throughput that is supported. And in this regard, the DPT creates two pipelines between the source and the sink node. Using these two pipelines, the source node is always transmitting the packet, and the sink node is always receiving the packet. All the intermediate nodes are either forwarding or receiving packets. And this means that all the nodes which are involved in the bulk transmission in the pipeline are always active. So this allows us to maximize the link layer throughput and achieve a high communication throughput. So on the slide here, we have one of the phases of the DPT protocol. The green-colored nodes are part of one of the disjoint paths, and the red-colored nodes are another disjoint path. The red arcs indicates the directional transmissions, while the blue arc indicates the directional receptions. The S is the source node, and D is the destination node. We want to transmit the packet in a high-throughput manner from the source to the destination. So at the time instance t equals to 0, the antenna at the source node orients its direction towards the first node in the red path and transmits the packet P1. The source node then receives this packet and immediately changes its antenna direction towards the next hop node and forwards this packet. In the meantime, the source also immediately switches its antenna direction towards the green-colored path and transmits the packet as well. And finally, the sink orients its antenna towards the red path and receives the packet, as well as there is transmission that happens in the other disjoint path. And all of these three transmissions happen at the same time on the same wireless channel using our protocol. And this is the next stage of the protocol where the sink changes its antenna orientation towards the other path and receives the packet as well. So all of these transmissions happen at the same time using the directional communication on the same wireless channel using our DPT protocol. However, this is not possible with an omnidirectional antenna, as it is possible that these transmissions might start to interfere with each other. And there are existing approaches like scheduling the transmissions in a way to avoid the interfering transmissions to happen at the same time, or to use the channel diversity to avoid this interference. However, the use of directional antenna allows us to actually reduce this interference, as well as to allow all the communication to happen on the one channel. And an important point of our protocol is that it doesn't need any explicit time synchronization mechanism. All the change in the antenna direction are triggered by the transmissions that happen from the source node. So there is no explicit need to have explicit time synchronization on the pipeline. So to have these disjoint pipeline operate, we need to understand what the network topology is like. This needs understanding of who are the neighboring node and what are the link configurations like. And this is extremely challenging because of the multiple antenna combinations that are possible between any pair of nodes in the network. As a link metric, for every transmitter-receiver configuration, we collect two metrics, which is one is the packet delivery rate, and the second is the received signal strength. And we use a protocol similar to SAND for collecting the link metrics. And all of this collected link metrics is sent to the sink node for further processing. Now, as we had discussed earlier, that all the transmissions happen together at the same time on the same wireless channel. This means that we need to identify transmissions which, if scheduled together, could interfere in time. And this is dictated by the fact that if they occur at the same time, as well as if the capture effect which dictates if the radio can receive the packet, it fails. So the capture effect is the ability of the radio to receive the stronger of the concurrently transmitted packet. It needs that the difference in the signal strength between the concurrently transmitted packet to be higher than a certain threshold, which for our low-power radio is 3 dB. So we pre-process all the link metrics that has been collected from the previous phase to find all the links whose difference in signal strength falls below this threshold of TC, which dictates if the capture effect can successfully happen. And we represent all of these links as a conflict graph. So the next step of the protocol is to use the collected link metrics as well as the conflict graph that we have generated to come up with the routing configuration which could allow us to have a disjoint pipeline between the source to the destination node. And we model this problem as a constraint satisfaction problem. So we give as an input to the solver to, the collected link metrics as well as the conflict graph. And our objective is to find the minimal cost path that connects the source to the destination node, but it has to satisfy the following three constraints. The first constraint is that we want to find a node as well as the link disjoint path. And this is extremely important since, as we had seen earlier, that all the nodes in the disjoint paths, they are always active, which means that we cannot share the same node for both the paths. So we need to find node as well as link disjoint path. The second is that we do not want to use any links which is present in the conflict graph at the same time because then they can interfere with each other. And finally, we want to ensure that the length of the paths differ by an even number. This is to prevent the transmissions to interfere at the sink node. We might also, as we had discussed earlier, that with the directional antenna, instead of one link between a pair of nodes, you can have k-square links between the nodes. This means that the problem could become significantly more challenging, and we might run into scalability issues because of the increasing number of links in the network. So the scalability could be affected by the number of nodes in the network, as well as the number of antenna configurations that are possible. And the solving time would affect the scalability of the problem. And hence, we propose heuristics to improve the solving time, which in turn improves the scalability of the problem. So in this respect, we analyzed 13 data sets from the real experiments that we conducted in this paper. And for each link in the optimal solution that we obtained, we ranked these links among all the possible links that exist between the same pair of nodes. And what we find is that the 25% or the 75% of the links in the optimal solution lie among the 25% of the highest ranking links in the network, which means that the links that ultimately form the part of the solution are the links which are of the higher signal strength. So we use this fact to come up with two heuristics. The first heuristic is the top M, which, as the name suggests, only keeps the M highest signal strength values between any pair of nodes in the network. The second heuristic is the weighted top N. Now, in a network with the ESD antenna, at max we can have k-square links between any pair of nodes. But in reality, the nodes might be deft in many of these configurations. So it's possible that some nodes might see more number of antenna configurations, and some might see only few antenna configurations where they are able to communicate with each other. To avoid penalizing the nodes which already see very few antenna combinations, we instead try to remove nodes in weighted top N from the nodes which see more than average number of antenna combinations in the network. And we only keep the N highest links in such nodes. So we then move on to the evaluation of our protocol. So for the ESD antenna, we use, as we had discussed earlier, the SPIDA antenna. So the SPIDA stands for 6 parasitic interference directional antenna. It is a electronically steerable, configurable, electronically steerable directional antenna. It has about 6 configurable directions, and each of the direction can be changed within few microseconds. So we can change the antenna directions at per packet basis. These are extremely simple and inexpensive and easy to make. In fact, the overall cost is less than $5 US and is dictated by the cost of an SMA connector. The antenna gain in the direction of the maximum antenna gain, the gain is about 4 dBi, and the energy consumption of the antenna is only in few microwatts. So we evaluate our protocol in 2 different RF environments. The first is the indoor environment of our office, which is about 32 square meter in area. As you can see from the image, it's a complex radio environment where there are metallic objects in the ceiling as well as in the corner. There are also other interfering wireless networks that are abundantly present, and this is much harsher than the expected environment for some of the bulk data transmission protocols, which would be characterized by a clean, interference-free environment. We also evaluate our protocol outdoors in an about 80 square meter of area in front of our main building. As our experiment setting, we did 23 separate experiments. We collect link metrics for an hour before we compute the disjoint path and start the bulk transmission. For the threshold to identify the interfering links, we set the threshold to be 6 TB. And for pre-processing to generate the conflict graph, as well as to find the disjoint paths, we use an iMac, which is equipped with Intel Core i7 with 16 GB of RAM for the pre-processing, as well as for solving. And each instance of the bulk forwarding, we send about 350 kilobytes of bulk data from the source to the destination node. So the first experiment we did was to evaluate the performance of the DPT protocol. So on the slide, you see a graph which shows the average throughput that we achieve for the different instances of the experiment. On the x-axis, you have the routing configuration where 3,3 indicates that there are 3 links in each of the disjoint path. The 7 indicates the performance of the DPT protocol over a single path. And what we achieve is that for almost all our experiment instances, we achieve a throughput which is greater than 200 kilobits per second, which is better than all the state-of-the-art bulk transmission protocols. We also achieve a packet reception rate which is greater than 90% in all the instances of our experiment. We see some CRC failures in our experiments, as you can see. This might be because interfering wireless networks are also present indoors, especially indoors when we are doing experiment, but this is not expected in some of the applications where bulk transmission could be used. The next experiment that we do is to look into the performance of the DPT protocol when there is a lossy link in the network. Even though we try to find the paths which avoids lossy link, but it is possible that the solution that we get might include a link which is lossy in nature, and this might be because there are no other options that are available. So to simulate this scenario, what we did was in the configuration shown on the slide, where there are 4 links on each disjoint path, and we try to send a packet from source to the destination node. At node 5, we drop packet at a rate of about 25%. So what we observe is that the throughput is is affected by the presence of this lossy link. The mean throughput is about 173 kilobits that we observe at the sink. And when the packets are dropped between the node 5 and 6, the throughput also suffers at node 6. This, as opposed to a mean throughput that we saw in the earlier slide of 200 kilobits per second, it is affected by the presence of the lossy link. In the same way, the packet reception rate is also affected, where we observe at the sink node that the packet reception rate is about 80%, and at the node 6, which is the next hop node for where the lossy link is present, the packet reception rate is at the order of 70%. But in spite of this, with the DPT protocol, even in the presence of lossy link, the throughput is still very close to the state-of-the-art bulk transmission protocol, as well as the packet reception rate is still greater than 80%. The next experiment that we did was to look into the effect of the link dynamics on the paths that are computed by the DPT protocol. So in this regard, we deploy 10 sensor nodes in our office environment, and we collect link metrics for over 24 hours. And we find at every 5 minutes the optimal the solution to the disjoint path problem. And we find the duration for which the solution remains usable, as well as the optimal solution. What we find is that the optimal solution changes quite often, especially during the day when there is movement in the office. But the paths remain usable for a long period of time. And when we say usable, it means that the constraint which dictate that the flows don't interfere with each other, it holds, and which means that if the bulk transmission is started, then it will happen successfully. In fact, what we find is that 50% of the solution that we obtain over a 24-hour period, 50% of the solutions are usable for greater than 55 minutes, which means that the link matrix collection could actually go a bit slowly as well. Finally, we evaluate the solving process. In this regard, we use the Minisync 2.0. in our experiments, the running time was not prohibitive. Still, we evaluate the performance of our heuristics. For the top M, we use the 2 parameter values of m equals to 5 as well as m equals to 10. And for the weighted top N, we use the parameter value of 25%. So this slide shows the results of our experiment. On the x-axis of the bar graph, you have the number of nodes in the network, as well as on the y-axis, you have the time it took to solve and find the solution to the disjoint path problem. What we find is that the running time is almost halved by using these heuristics. And there is a higher improvement as the number of nodes in the network increase. But what is more important is that for our heuristics with the parameter value of m equals to 10 and n equals to 25%, the optimality of the solution is not affected. That means that the solution that we obtain has the same cost as the optimal solution. However, in reality, these heuristics provide a knob which the deployer of the application could use to improve the solving time and look at the trade-offs. Finally, we look into comparing the throughput that we achieve as compared to the other bulk forwarding protocols. So one of the problems with the existing bulk forwarding protocols is that they are not designed for the ESD antenna, with the ESD antenna, and it's not possible to redesign them to be able to exploit all the features of the ESD antenna. And hence, we only compare against the highest reported numbers from their respective publication to compare the results of the DPT protocol. What we find is that the throughput that the DPT achieves outperforms all the existing protocols in terms of the throughput, as well as the number of nodes that are required. The P3 is the closest protocol in terms of the throughput and the design for DPT, but it needs multiple channel to operate, as well it needs higher node density to operate. So in summary, we present DPT, which leverages ESD antenna for bulk data transmission. We experimentally show in a real testbed that the directional transmissions and receptions reduce intrapath and interpath interference significantly. We show that this reduced interpath as well as the intrapath interference allows us to have high throughput multi-hop transmissions happen on the only one wireless channel, and we achieve throughput that is close to the maximum supported over the link layer. Thank you, and I'll take the question.